What does the quiz question ask? Today's was one of the simplest quizzes, right? Quiz number 27. Now, apparently Bilkent Radio keeps repeating that it's 96.6 MHz. What does that mean, MHz? Megahertz. And what is, and they're doing their broadcast on electromagnetic waves. So what does this tell us about the electromagnetic wave their transmitters are sending us? This is the frequency, right? Omega or nu? Angular frequency or the usual frequency? Okay, the usual ordinary frequency. So nu is 96.6, 10 to mega means 6, 10 to, no, giga means 9. Okay, hertz. That's great. So how do I find the wavelength? That's the first question. What's the wavelength of the light? Wavelength of the electromagnetic wave carrying Radio Bilkent's free broadcast. How do I find it? I said the frequency, angular frequency was c times k. Omega was 2 pi times nu. C is c. K was 2 pi divided by lambda. 2 pi is cancelled. So in other words, lambda is c divided by nu. C is 3 10 to the 8 meters per second. Nu is 96.6 10 to 6. What was hertz in base units, our basic units? 1 over seconds. So these cancelled. So let's see. I'll use a glorified calculator. 3 10 to the 8 divided by 96.6 e to 6, 3.1 in which units? Meters. Okay, so it's apparently Bilkent radio waves are at exactly, where's my notes? Okay, 3.1 meters wavelength. So that's actually pretty long, right? I mean, it's 3.1 meters, something like from the ceiling to the floor, I would say. Most of our receivers, antennas, FM antennas, are actually shorter. So engineers have found better and better methods of coupling or generating electromagnetic waves or listening in electromagnetic waves. So still, you cannot make a very small radio receiver. It will not be very efficient. If you want to efficiently couple to the electromagnetic wave, your antenna size should be comparable to the wavelength. Okay. Generally, the best antennas are at half wavelength or quarter wavelength. Okay. Quarter of this 3.1 meters would be something like 75 centimeters. You know, and when some of your phones may have FM radio in them. When you try to turn on FM radio, what does the phone say? That's right. It says plug the earphones, which is going to act as an antenna. Why? What's all time? From here to presumably your pocket, that's around 30 to 50 centimeters. That's closer to quarter wavelength. All right? Good. Now, how long does it take for the electric field in that wave to complete one oscillation? What's this asking in terms of the properties of the electromagnetic wave? It's asking the period, which is 1 over the frequency. So it's going to be 1 over 96.6 10 to 6. 10 to minus 6, or I'll say, I'll not calculate it with a calculator, I'll do the following. This is almost 10 to minus 8 seconds. Or I can say it's 10 nanoseconds. I'm right here, right? There's nothing wrong here. 10 nanoseconds. That's pretty short time. So megahertz frequencies are radio frequencies, and we'll see in a moment, okay, part C, based on the size of our cellular phone. So our cellular phones nowadays, they are getting bigger for different reasons, for higher, bigger screen reasons. Everyone wants to watch movies on their cellular phone. So I would say the size is around 10 centimeters. So I would say maybe lambda should be of order of 10 centimeters. I mean, it's not going to be 5 meters, obviously. Okay, then you cannot actually couple to it. Even FM radio wants you to put on your earphones. So lambda of the wavelength of the transmission of the cellular frequencies must be around 10 centimeters. Maybe it will be 50 centimeters, maybe it will be 2 centimeters, but 10 centimeters should give us an order of magnitude. It's not going to tell us exactly which frequency they are operating, but nonetheless, so let's take lambda to be 10 centimeters. If lambda is 10 centimeters, what is the frequency? Frequency now is going to be C over lambda 3 10 to 8 divided by 0.1 meters, that's meters per second. So it's going to be 30 10 to 8 hertz, or 3 gigahertz. So for oscillations around at the gigahertz range, apparently the wavelength of the electromagnetic wave is at the order of 10 centimeters, at the order of centimeters. Okay. Now, I asked the question last time. I asked, why did people not have cellular phones right away? They could get radio transmission. You know, even as early as 1910, I think, there was radio transmission in Europe. You could listen to radio. Why didn't they have cellular phones right away? Because they did not have the oscillators. They could not handle, the electronic circuits could not handle oscillations which are that fast. All the electronic circuits, essentially before 1950s, relied on devices called vacuum tubes. And vacuum tubes had very nice properties. The only problem is that when you try to force them a little bit above kilohertz range, even in the megahertz range, they had trouble. So even FM radio was not very reliable because the circuits were not very reliable. Once the transistors came into play, the silicon transistors came into play, it was possible to build these megahertz oscillators as material science, as the physics of what's going on inside the transistor improved. As we understood it better and built better transistors, we get to higher oscillators, higher frequency oscillators, which shrank the size of the circuits, which made things like cellular phones possible. All right? Any questions? How about the following question? How much power do you think Bilkent radio is pumping into the air? Does it have anything with the frequency? So I said electromagnetic waves can carry energy and momentum. maybe you've heard about things like, come on. Maybe you've heard about things like 10 megawatt station, or like 100 megawatt station transmitters. Okay, let's, for a moment, I'll try to pair my pen again. Okay, so let's talk more about energy in electromagnetic waves. How do I create electromagnetic waves? That's one thing first I would like to talk about. How does one create electromagnetic waves? And here's the, if you want, the upshot of how that happens. Sorry. What do we need? What's going on in an electromagnetic wave? What was our physical picture? There's a changing magnetic field which creates a changing electric field, which creates a changing magnetic field. So there is this feedback mechanism. But that needs a mechanism to start it. How do I actually start an electromagnetic wave? And I'll actually give you a simple explanation. Now, if I have a point charge, let's see, Q. If it's just sitting there, what do the electric field lines look like? They are just going away from my charge. Are there any magnetic field lines? Not at all. So let me do the following. Let me start moving this charge with velocity v. And look at delta t after movement. Now, my charge will now have moved. So this was the original position. It will have moved by delta t times v. But what do the electric field lines look like now? Now there is an important principle in physics that was found by Einstein. And it's the basis of relativity. The speed of light, which we have derived in terms of epsilon 0 and mu 0, is an absolute speed limit in the universe. No information can be transferred faster than speed of light. Okay. For example, if the sun somehow got extinguished now, we'd only learn about that in 8 minutes. We are 8 light minutes away from the sun. So the same thing here. If my charge started moving, there will be a region of radius c times delta t, which will know about this motion, but all the region outside the sphere will not know that my charge is moving. Okay. What will happen is that outside that sphere, my electric field lines will be just the old field lines of the charge which was not moving. But now, if I actually go closer to the charge here, I know that near the charge, again, field lines must be emanating from the current position of the charge. So the outer sphere is like a hedgehog with the center at the old position. Nearby, it's like a hedgehog at the new position. So how do I make these lines continuous? And here's what happens. I am going to connect them. I mean, that's the nice, beautiful thing about if I draw the same number of lines. Well, what will happen is that these lines, especially near the edge, they will start to bend. Okay. Not only that, what does a moving charge create? Not only electric field lines, it starts creating magnetic field lines. What kind of magnetic field lines do they create? The magnetic field lines, which now I have to do in another color. Let's do it in orange. The magnetic field lines, because this is the velocity, they are going to circle my charge. So what happened now? In the region here, I have an electric field going one way and magnetic field perpendicular to it. Whenever I have time rate of change of electric field, that's going to create another B field. So once, if at some point I can get time-dependent electric and magnetic fields perpendicular to each other, that will start a feedback cycle. And that feedback cycle is going to give me an electromagnetic wave. So what will happen is that I'm going to just highlight it. There will be a radiation region. Around an accelerated charge. So our important principle is going to be simple. Accelerated charges create electromagnetic fields. Now, after Maxwell's theory took time for physicists to think of a scenario where they can actually accelerate charges. And then there were a lot of developments in technology by then. Then someone realized, Hertz realized, that what happens if I apply AC voltage to a piece of metal? What I apply when I apply AC voltage to a piece of metal, electrons inside that metal are not really going from one edge to the other. What do they do instead? They are oscillating, right? That's what's happening. Okay. So if you're actually driving an AC voltage here, your charges here at the two edges, they are essentially just oscillating. Okay. All your electrons are oscillating, and which means if they are oscillating, they are also accelerating. They must be stopping and starting. So a configuration like this is going to create electromagnetic waves. So this is going to be the first antenna. Okay. Now, the design of antennas, the things that can create electromagnetic fields efficiently, is a major design problem in electrical engineering. I think there are not many electrical engineers in this section, but those of you who are in electrical engineering will have to deal with this problem in the third year and maybe in the fourth year, depending on what you work on. But all cellular phone manufacturers, they actually have to think, they have to put antennas into your cellular phone, and they cannot just put one antenna. What do they, 900 megahertz is the frequency for your GSM communication. What else do they need in there? What does your cell phone communicate? What other frequencies does it actually vary about? It varies about Wi-Fi frequencies, okay? Which is a little bit actually lower. It's around 100 gigahertz, okay? It also varies about other kinds of wireless communication, like no, GPS is it's completely different. Okay, it's almost like a radio wave coming from above. Yes, Bluetooth, right? That's another frequency. So on your average cell phone, with average today cell phone, there are 5 or 6 different antennas for all these different frequencies. Okay, there are so many of them. If you actually there is so much metal in a cell phone. If you try to use your entry cards, any kind of wireless communication system can be blocked by a cell phone. Okay, inadvertently they act like near-field Faraday cages. So whenever I have a car which has a wireless entry system, if I put the cell phone with in the same pocket with the key, it basically blocks the key. So it's acting like a jammer. Now, here's an interesting thing. I talked about Radio Bilkent. Nearby there is another radio. Nearby there is another radio. And then I talked about Wi-Fi frequencies, TV frequencies. Do you know who regulates all this stuff? Clearly, if I put a transmitter here, start transmitting at 96.6 megahertz, what would that cause? What will happen to that? What will happen? Now you probably are way too young to remember. I don't know if you were even on this earth when this happened, but around 1990s, sometime, up to that time, there was only a single radio station and a single TV station in Turkey. Well, there were 2, but order of magnitude is right. Okay. So what happened is that suddenly, without any laws being passed, the government said, okay, we're going to allow people to open up radio stations. And so at that time, the radio waves were very lively because you didn't know which channel you're going to get it at which frequency. Anyone who had the most powerful transmitter got the frequency. Okay, so you could tune into, I don't know, so you try to tune to Bilkent radio, but that day some other station decided to basically transmit at that frequency, so you would start hearing, I don't know, Ankara havaları at the same frequency. Okay, and then when you travel from Bilkent to Kızılay, you would start hearing a different station because you were closer to that station's transmitter. Finally, there was a law passed, and Bilkent actually had a big part in frequencies were basically sold by bids. Okay, people bid for different frequencies, and right now it's actually unlawful to transmit at these bidded frequencies. Frequencies are bought. Maybe you remember there was very recently some new frequencies were opened up for what's called 4G, for new technologies, a little bit higher in the gigahertz range. So it's actually quite, it's really funny to me. Somehow, in the old days, it was only basically piece of land that could be rented or bought. Right now, the government is renting frequencies, and it's just like it's illegal to go into some government property. It's illegal. There are military frequencies. If you get a transmitter or receiver at that frequencies, that is a crime under the law. I mean, you could be, jailed for having such a transmitter. So, how do these? Let's go back to this issue of power. How much power do I need to, let's say, transmit my radio station from Bilkent to Kızılay? How would I determine that? What did we say about what a general electromagnetic wave looks like? Let's remember this. Electromagnetic wave let's say that it's going in some direction k hat. What do the electric fields and magnetic fields look like? There will be a peak electric field, cosine. Now, I'll write this in an interesting way. I'll say this is r dot k. Okay, k is my propagation direction. K is in my propagation direction, and the length is 2 pi divided by the wavelength minus omega t, and the magnetic field is going to be B0 omega t. Now, what? That's okay. That's the general way an electric field and a magnetic field looks like in an electromagnetic wave. But not all the symbols here were independent. First of all, we know that omega must be c times k magnitude. And furthermore, we know that the peak electric field magnitude must be c times the peak magnetic field. And furthermore, we know that the direction of propagation is perpendicular to both the electric field and the magnetic field. So the direction of E cross the direction of B gave me the direction of propagation. Now, how about power? How much of the energy is transmitted in electric field, and how much of it is transmitted in the magnetic field? We've calculated that, and what did we find? We find that it was actually shared half and half between the electric field and the magnetic field. Now, here comes a nice way of thinking about that. What is the energy transmitted per unit area per unit time by an electromagnetic wave? So essentially, I'm asking the following. I'm saying if I take an rectangle of area A with area vector A, and I'm going to take this rectangle, paint it black so it absorbs all the electromagnetic wave falling on it. Okay. I'm going to show it to the sun, and I would like to understand how much it will heat up, or how much power it's going to absorb per unit meter square. And the answer, it will turn out, is very simple. I'm going to call this P. It's going to be a vector times dot A. Obviously, that there is the dot product. My area vector should look at the sun if I want to absorb more energy, right? If I have a solar panel, it should face the sun. That's why I have the dot product. But what's this S vector? S vector is the energy flow in my electromagnetic wave. And it has a very simple formula. 1 over mu 0 E cross B. Okay. This is called Poynting vector after the physicist who first defined it. Okay. Now that's good. So what's the unit for this? What's the unit for S? That was going to be your next quiz question actually, but let me, now that I asked it, let me answer it. What's the unit for S? How did I define it? So S dot A is the total power absorbed in an area. So what should be the unit of S? Watt per meter square, or joule per second per meter square. Okay. Does it make sense? And that was what the quiz question will be. What is the unit for mu 0? What's the unit of E? And what's the unit of B? If you multiply them out, do you really get watt per meter square? Now, I may change the question. Maybe I will not do. Now, how about momentum now? And here comes the interesting thing. S, the Poynting vector, also tells us about how much momentum is carried by an electromagnetic wave. And here is the interesting thing. If you calculate how much momentum an electromagnetic wave is carrying, you find a very simple result. Momentum carried by an electromagnetic wave per unit area is just going to be 1 over c times the Poynting vector. Or in other words, for an electromagnetic wave, energy is just c times its momentum. Okay. Energy carried by an electromagnetic wave is c times its momentum. So here is the question. If we have a 10 watt laser absorbed by a black, okay, I'll say black body and then I'll tell you what that means, with mass m equals 1 gram, for 1 second, what is its final velocity? So here I am putting a small particle and I'm shining a laser beam on it for 1 second. And because it's absorbing all my laser beam, it will start moving with velocity v. So I would like to understand what's the velocity of that particle at the end? Now, my initial laser beam had energy, but it also had momentum. Do we know that momentum is conserved? Yes, we do. So if all the momentum in the electromagnetic wave is absorbed by my black body, then my final momentum must be equal to the whole of momentum of the laser beam. So I'm going to say m dot v must be equal to what? M dot v must be equal to 10 watt laser beam. So basically the total power times delta T, that's the total energy inside my laser beam. And if I divide this by C, what do I get? I get the total momentum contained in the electromagnetic wave. Okay, so let's do it. P I gave you as a 10 watt laser beam. Delta T I said is 1 second. C is 3 10 to 8 meter per second. This is 10 watt, so this is joule per second, is kilogram. So this is 1 gram particle. 1 gram particle is 10 to minus 3 kilograms times V. So V is what? 10 divided by 3 is almost 3. Okay, so 3.3 10 to minus 8 10 to minus 5 meters per second. Maybe not so fast, right? I mean, the problem with the scales we are interested in, if I have something of the scale of 1 meter, the energy component of the electromagnetic wave is very important. The momentum is energy divided by C, right? So momentum component doesn't seem that important if I just look at the units. However, actually, if you go to smaller and smaller particles, the momentum component becomes as important as the energy component in some systems. And there are really nice proposals of propelling particles, especially in space, by shining laser beams at them. And there's actually a project, a competition, to send a small object as high up as possible using lasers. Okay, and a lot of groups are trying to do that. So that's one thing maybe you would like to try as engineers. Okay, how can you actually accelerate or force objects using laser beams? Even more interestingly, if you have electromagnetic waves, you can use them to apply forces. If I have a mirror which is reflecting my laser, there must be some photon pressure, light pressure on that. If you have very small objects of the order of micrometers, then that's a sizable force. That's a quite important force on it. Now, one of our faculty members, Giovanni Volpe, has a big lab where he studies what's called optical tweezers. Do you know what a tweezer is in Turkish? Cımbız. Okay. So what he does is he crosses two laser beams and creates a region. And by changing this region, he can actually pick small objects up and move them. He can apply forces on small objects, of micron-sized objects. So one of the most interesting experiments done with these optical tweezers in his group was they measured how much force a small bacteria applies to swim. Okay, how do they swim, right? So what they do is they basically use the tweezers to constrain this poor guy and put some food here. So he's trying to get to the food, but he cannot get out of the tweezers. So they tune down the electromagnetic wave a little bit. So less force, there will be less force. At some point, bacteria can swim out. So you can actually measure how much force all these microorganisms can apply inside water. That's I think quite remarkable. People are actually thinking of making, one of the best science fiction inventions is a tractor beam. In Star Wars, there's a tractor beam on your spaceship. You can't move anywhere. You're just basically being pulled around that. That's not super science fiction. If you had big enough lasers, you could do that. One problem though is that at the scales we are interested in, if you have a spaceship, those lasers would probably vaporize you before they actually transported you to some ways. So this is all I want to say about electromagnetic waves. On Monday, before you go, you pick up one quiz from here, and on Monday you'll bring this quiz back and we'll do an exam review, a review for the final, okay? See you on Monday.